lucky today to have one of our very successful stars from Santa Barbara. I can say that because he was my student. He was here before I was, actually, but he was an undergraduate and joined my group soon after that. Worked on VCSELs, and then we wrote a book together. And the more complex parts of the book are due to Scott. The harder homework problems.
Sorry, guys.
But Scott joined Agilent HP, I guess, at the time, soon after leaving here, and got a little involved in the nitride work there, and did a little bit of homework, and I guess some of that and some of what's happened since he's going to talk to us about today. And just coincidentally, there's been some news about nitride lasers here recently, and of course we have with us recent Nobel laureate, Shuji Nakamura. And Shuji will probably add any corrections that are necessary.
Absolutely. Looking forward to it.
So, Scott, I'll turn it over to you.
All right. Well, thank you all for coming. It's nice to be back here after a long hiatus. But just to put into pictures what Larry mentioned before, this thing will work. Okay. Oh, whoops. Okay, so, all right. So, as Larry said, I was at UCSB, start to finish. I was pretty much a lifer, and just to prove it, come on. Okay, maybe I'll just. And just to prove it, I scanned this is my freshman student ID card, 1981. Keep in mind it was 1981. The hairstyles were a little different back then. And then after 4 years at UCSB, I was transformed into this person here. You notice shorter hair, but kind of a dazed look there. So I think that was from the 4 years in undergrad at UC Santa Barbara. And of course, I stayed on to do my PhD with Larry. This is in his backyard, PhD graduation. And of course, we worked on the book together. There's a picture of me under the coffee table under the final edit of the book. I put final in quotes here because I don't know for sure, but I'm guessing this probably was not the final edit. Okay, so let me just give a little preamble about what this talk is about. After I left and we finished writing the book, I went to HP Labs, as Larry mentioned. And shortly thereafter, Rick Schneider came to the group, and he started up a gallium nitride blue laser effort on the heels of hearing all the news of Shuji Nakamura's success with lasers. And so there was a small effort there. I was peripherally involved. I wasn't in the group, but I was certainly tracking their progress. And then at the end of 1998, 1999, we were asked to give a short course at the SBIE conference, which is local up in San Jose. And for that course, I ended up doing a lot of literature searching, and that's when I truly, learned to appreciate all of the work that Nakamura had done in the late 80s on lasers. So I kind of became obsessed with tracking all of the papers that he did, and as well as papers from other groups. And I documented some of that as part of the short course, and it just seemed appropriate to go through some of that here, given the recent news. All right, so, and just let me emphasize that the slides here for the first part of the talk are all from that 1999 time frame. So these slides are all put together in 1998, 1999. Of course, a lot of things have changed in the last 15 years, so a lot of things here might be outdated. But think of this as kind of a retrospective snapshot of the state of things at around the 1999 time frame. So an outline of the talk, I'll go over some motivation, which is kind of funny to see now from 15 years ago, what we thought they would be used for. Some of the challenges, and then I'll go into some of the details about what the differences are from making gallium nitride lasers compared to more normal semiconductor lasers, normal, standard. And then I'll go over some of the accomplishments, particularly of Shuji Nakamura, as well as what other groups have done, including UCSB. And then I'll add some things that have happened more recently, first within the next 5 years after '99, and then, of course, what just happened a few weeks ago. So at the time, this was kind of the perception of what blue lasers might be used for. The DVDs was a big one. Laser printers, people thought they'd be used for, as well as color displays. And 15 years later, DVDs are the real commercial success. I think there are certainly other things that are happening. And of course, lighting now. But at the time, this is the one that took off. So what I'd like to do is just show a few of the basic components of a semiconductor laser, and then we'll go into the details of each of these components and compare them to normal lasers. So you have your substrate, you have your epi layers, and then you have your optical cavity, lateral processing, as well as mirror facets that has to be done. And then you have your electrical connection, of course, to the laser. And so if we start with epi material requirements for making a laser, we need to have an active layer that has a direct bandgap semiconductor in the desired wavelength range, of course. And so if you look at the periodic table, I think you all know this, but the group 3, group 5 elements are listed here. You can also pair up the two 6s together. And as you climb your way up the periodic table, the atoms get smaller. As the atoms get smaller, it's kind of like having narrow quantum wells. The energy levels separate more, and so your band gap gets larger. And so as you move up the periodic table, you get to shorter and shorter wavelengths, larger and larger band gap. And if you arrange the group 3 and group 5 elements into a matrix, you can arrange them like this, and you see that they get roughly arranged into the antimonides, the arsenides, the phosphides, and the nitrides. And of course, we're talking about the nitrides here. As you move from the bottom over here to up here, you go from long wavelength to short wavelength. And this is where you can really access the visible range. The other materials are very common for other applications, but you can't reach blue or green. Another thing that people have tried is 2,6 materials using zinc selenide and cadmium selenide mixtures. But common lasing wavelengths are for indium phosphide. You can get to about 1,200, 1,600 nanometers. It's common for telecom and datacom. And then if you want to move down to AlGas, you can reach the 700 to 1,100 nanometer. This is good for CDs, laser printers, datacom. And then going further down to 620 to 690, you have DVDs, laser printers with in-gap. But if you want to go below that, it's difficult. There are different options at the time. One of the common ones is frequency doubling of gallium arsenide type lasers. That gets you into the 400 to 500 nanometer range, but this used bulky, complex external optics. Another one is zinc selenide, as I mentioned. But this isn't quite blue enough. In addition, they really struggled with getting the lifetimes up. So it was really not the best option. And then gallium nitride seemed very attractive. So there was a lot of success in the LED work, and so making lasers out of the same material seemed very, very interesting. In particular, if you look at gallium nitride bandgap all the way to indium nitride bandgap, it spans pretty much most of the visible spectrum of it, which of course is why LEDs are of much interest for gallium nitride, but lasers as well. But for DVDs and for Blu-ray discs and things like that we know of now, you're really more interested in the bluer side, the shortest wavelength you can reach. And so blue, especially in the 400 nanometer range for gallium nitride, was a kind of a sweet spot for what people were interested in. So an additional thing that you need is cladding layers. You need a compatible higher bandgap semiconductor. And this is something that's a little different than with LEDs. With LEDs, you don't need to worry about this so much. But for lasers, you need to have really good electron confinement because your carrier densities are very high. Your carrier densities are very high. So you really want to keep those electrons in the active region. So it's usually you have an active layer of barriers on either side and then a cladding on either side of that. And you really want to prevent, you want to dump electrons into the active region, but you want to prevent them from leaking out. So you want a very large band gap offset here. So for that, you really need a higher band gap cladding layer. In addition, you want to have good optical confinement. Again, something that's not really a requirement for LEDs, but for lasers, you need to have a good vertical confinement. So you again want a low index cladding layer to confine your mode nicely. Now, if we look at our standard materials, AlGas, indium gallium arsenide phosphide, you have readily available AlGas, which can be used, which is much higher band gap than gallium arsenide, and can provide the cladding layers that you need. And same with InGas, you have readily available cladding layers all the way up to indium phosphide. So very nice systems for making lasers. And of course, there's been tremendous success with that. When you look at the Al-InGaN material system, if you look at the band gap as a function of lattice constant, you see that it's a lattice mismatch system. Aluminum nitride has a smaller lattice constant, indium nitride has a much larger lattice constant. And so if you want to try and go to higher band gap cladding layers and you want to follow the ternary Al-GaN, you have no choice but to put strain in the material relative to gallium nitride, and which is something that's different than you have with gallium arsenide or even InGaN. And likewise, if you want to make the wavelength a little longer, you have to go along the InGaN line, which adds positive strain. Of course, it would be ideal if you could actually make a quaternary here, but no one at the time was very successful at making quaternaries. And the main reason is that the algan is grown at very high temperatures and the ingan is grown at lower temperatures. So there were just no good growth conditions for giving you very successful, good quality quaternary material. And so most people ended up using algan to make the cladding layers. But you were pretty much limited to something less than 20% before strain caused a big problem. And so if you just look at conduction band offsets in normal materials, you're looking at a few hundred MeV. And you contrast that with ingan, or especially with algan, where you want to make your cladding layers, you're looking at 1 to 200 MeV. It's not nothing, it's not zero, but it's not the same amount of delta UC that you enjoy with these other materials. And particularly, if you want to boost up the delta UC, you really have to increase your aluminum mole fraction. Again, something that's not really a requirement for LEDs, so something unique to making lasers. And one method to reduce the leakage, introduced with Shuji Nakamura, is this electron blocking layer that's put on the one side of the active region to block and keep electrons in the active region. You may remember this. This became ubiquitous. Pretty much everyone started using this, and it seemed to work fairly effectively. And so if you then look at index differences of the different materials, again, the standard materials enjoy very large delta N's, and so you can make very nice waveguides vertically. In the algan system, you really got to crank up the aluminum mole fraction. Even at 20%, you're only looking at 0.12 delta N. And so it's not very large, but nevertheless, you can still make confined modes with algan. But you need to go up to, say, 0.15 aluminum mole fraction to get a decent mode. You can live with 0.05, but there's a trade-off here, because the lower the aluminum mole fraction you have, the smaller the delta N, and the wider the mode will spread out. And when you grow these structures, you want to make sure that your algan is thicker than that tail of the optical mode. So if you do choose to go with 0.05, you're going to have to go with more than a half micron of material. If you go with 0.15, you can get away with maybe 0.3 microns. And so there's a strain thickness trade-off there that has to be balanced. And so depending on the material quality that you're growing, your choice of cladding aluminum mole fraction was pretty key. So the next thing for epi is the substrate. We have to have a suitable substrate for good epitaxial growth. And this is, again, common material systems. You have gallium arsenide substrate for algas, and you have indium phosphide. And this works great, as we all know. You can have very nice lattice match systems. When you go to gallium nitride, you have sapphire and silicon carbide. And both of these are heavily mismatched from gallium nitride. Sapphire in particular, I put close to 14%. Silicon carbide is a little better than that, about 3 to 4%. But both this extreme lattice mismatch required a buffer layer to be grown in between the gallium nitride and the sapphire. And so this is an example of gallium nitride growth on sapphire. So when you're growing on sapphire, you needed a low temperature buffer layer, which was developed both by Amano as well as Nakamura. But even when you do this, you still have very high dislocation densities, in the range of 10 to the 9, 10 to the 10th per centimeter squared. So you worry about carrier recombination, you worry about scattering, optical scattering, you worry about reliability. So clearly it's not ideal. Then comparing silicon carbide to sapphire, there's some advantages with silicon carbide. It has a conductive substrate, so it allows for vertical current flow. You have single top contact, better thermal conductivity than with sapphire. However, the substrate's very expensive, and so that's what's kind of a limiting factor for using silicon carbide. Gallium nitride laser on sapphire, it's an insulating substrate, so it requires 2 top contacts, there's poor thermal conductivity, poor cleave facets, as I'll show you in a minute. But best devices are still made, well, at the time, were still made on cheap sapphire substrates. So let's move on to the cavity requirements. And so I've talked about the vertical waveguiding. We also need lateral waveguiding. And there were different options at the time. These are pretty standard, even in standard lasers. There's gain-guided structures that are very simple to make. You just put down some metal here, and you got to have your 2 contacts, no etching required. But it's poor confinement for the carriers, as well as for the optical field, high thresholds, and low efficiencies. And if you go with a striped structure, which I think Nakamura started out with, a deep mesa structure, it has good confinement, low threshold, but it's multi-mode, and it has poor heat flow, so not the best for a CW. The ridge structure is kind of the ideal case, because you can just etch down through some of the P material. You can get good confinement of the current. You also get good optical confinement, and it's really the best situation. You get good heat flow. and this is what Nakamura ended up using later on for some of his better devices. Not that the first ones weren't good. But, anyway, so sidewall etching was another thing that was kind of challenging. The material is much stronger, so people developed ways. It's actually fairly standard methods, but it was slower etching, so getting etch selectivities was a bit challenging. I think these days it's pretty routine. But nevertheless, even at that time, people were able to get pretty nice sidewalls in gallium nitride. And I mentioned before the ridge laser's advantage because you could get good current confinement as well as optical confinement. But Nakamura optimized the structure so you could actually get single mode, 70 milliwatts single mode behavior from one of these ridge structures. So very nice single mode behavior. And one of the things though is you have to do etching of the sidewalls here. And I just threw in this plot because it's a nice segue to the next thing I'm going to talk about is this. Sometimes you can have pretty bad sidewalls. This is not from Nakamura's publication. But scattering losses are a big deal. You have to worry about losses, both absorption as well as scattering losses in the laser. Again, it's a different thing than working with LEDs. You have your mirror losses, but with internal losses, you have both absorption and scattering. The scattering can come, of course, from you have defects that are grown as well as on the sidewalls, but absorption can be a big problem as well, especially in InGaN. If you look at, gallium nitride, if you look at AlGas, your internal losses are generally in the range of 3 to 10 inverse centimeters. At the time, the InGaN, AlGaN structures were in the 35 to 50 inverse centimeters loss range. And it wasn't just free carriers in the dope layers, but it was also absorption tails that were occurring in the transparent layers. And this is an example of one person's. Of course, I'm sure these plots vary wildly depending on the material quality, but this one particular example shows material losses in the AlGaN layer in the hundreds of inverse centimeter range. And so with this type of structure, it's going to be very difficult to make a laser because the losses are just so high. Getting good external quantum efficiency is very challenging. So then finally, for the cavity, you want to have good optical feedback. So you either have to have crystal facets or distributed reflectors. Cleaving gallium nitride on sapphire, then you may think it seems like it should work. Gallium nitride should just align on sapphire, and then you can be able to cleave along one of the planes. Unfortunately, it twists a little bit when it actually gets grown on there. And so some of the cleavage planes on sapphire are the A face and the M face. And what you end up with is because it's kind of a terraced face here that has some roughness to it. So getting good reflectivity is a bit challenging on sapphire, on C face. Alternatively, if you're growing on silicon carbide, it's much easier. You can cleave the gallium nitride and get very nice, smooth quality cleave facets. So people who are growing on silicon carbide generally cleave their facets. Another way to do this is through dry etching. A Bear from Santa Barbara is one of her pictures here showing some nice dry etching of the sidewalls. And Nakamura also did that in the beginning with dry etched sidewalls, dry etched facets. Other people with Zrock, they've managed to actually make third-order gratings and make VFB lasers out of gallium nitride. So moving on from cavity requirements, there's also performance requirements. Requires high optical gain, small effective masses, which can lead to low threshold currents and high differential gain. If you compare standard materials to InGaN, with gallium arsenide and InGas, they really enjoy very small conduction band masses, effective masses. Heavy hole masses were larger. But if you look at InGaN, the situation is quite a bit worse. And what this leads to is much higher transparency carrier densities. You're talking, instead of being in 1 to 2 times 10 to the 18th per centimeter cubed, you're talking about 10 to the 19th, probably an order of magnitude, maybe a factor of 5 higher than gallium arsenide. Transparency currents were higher. Differential gain was a factor of 5 lower, perhaps, based on just theoretical estimates. However, even with this, some theoretical estimates of gain show that you can actually get decent gain curves out of InGaN, just from the theory. So you should, 40 inverse centimeters is plenty to get decent lasing if your internal losses are kept low enough. However, theory is kind of different from experiment in gallium nitride, because in gallium nitride, the quantum wells, the InGaN quantum wells, are not ideal. They don't behave the same as gallium arsenide or InGaAs quantum wells because there's additional components. There's indium clustering was suspected. Localized transitions could be occurring, quantum dot effects. Piezoelectric field is strong in strained InGaN layers. And people were observing strange low-energy gain spectra, as well as just low-energy emission from LEDs as well, that was suspected to be due to polarization fields that would exist in the InGaN. So at the time, simple gain theory calculations of this material system were not sufficient to really capture the gain properties of the materials. So another big issue for gallium nitride is the doping. Voltage drops in laser structure. Of course, you have your standard P contact, P spreading layer. You got your N spreading layer. Spreading. This is just your cladding layer and cladding layer resistance, and then your N contact resistance here. And those all add up. You'd like that number to be as low as possible. If you look at dopant material choices, for gallium arsenide, you've got a whole host of dopants that you can choose from. High max concentrations can be achieved at low activation energies, very, very small, very easy to ionize. N-type, you had a couple of choices there, also very good. If you look at gallium nitride, the N-type is also very good. You can get very nice activation energies, max concentrations are very high, so N-type doping in gallium nitride is not a problem. The real big issue is P-type doping in gallium nitride and InGaN, which Shuji can tell you all about. The magnesium was the dopant of choice, and it has very large activation energy. The max concentration levels were not that high, especially when you're considering that you need to get to 10 to the 19th for transparency. And the news gets worse as you go to the cladding layers, where you really want your P contact or your P layer to be highly doped. It just gets worse, the activation energy. So it became more of a problem as you went into your cladding layers. And as an example, P gallium nitride would have a resistivity in the range of 1 to 2 ohm centimeters, which translates into just a few tenths of a volt at 1 kiloamps. So for LEDs, this may not be much of a problem. But if you go to AlGaN, you're looking at a factor of 10 higher than that. And so 1 to 2 volts at 1 kiloamp. You can have as much as that. The other issue is ohmic contacts. For gallium arsenide, gold zinc works great. N contacts, this also works great, 10 to minus 5, 10 to minus 6. For gallium nitride, again, the N side is fine, pretty similar to gallium arsenide. But if you look at the P side, you're looking at maybe 2 to 3 orders of magnitude worse contact resistance. So this was just really a killer for gallium nitride for quite a while. So at 10 to the minus 3, this translates into, for typical laser dimensions, about a volt at 1 kiloamp per centimeter squared. Which again, you may not think that's too bad, and for LEDs, this may not be so bad. But if you're looking at a laser, which you're wanting 10 kiloamps per centimeter squared, it adds up quickly. And so if you kind of revisit that chart I had before, you're looking at 10 volt drop just across the P contact. Then you got another 5 volts in this P layer up top here. So 15 volts just in your P side here. The inside is actually not so bad. And when you add it all up, you're looking at 19, 20 volts. And this was a problem that a lot of people struggled with. And one problem that actually Nakamura found a solution for. And he was ahead of the game. So finally, performance requirements, of course, for CW operation and commercial realization, you want robust, reliable materials. And AlGas, you have oxygen contamination because the aluminum, non-radiative recombination, which can occur, laser facet damage, or typical issues. For gallium nitride, of course, we worry about the high dislocation densities. However, defect propagation is slower in gallium nitride. It's a tougher material. Defect recombination rates are slow as well. So even though the defects were very high, it was mitigated by some of these. So actually things weren't quite as bad as you might think. But still, there's definitely a desire to minimize the defect density. And so one of the techniques that became popular was growing SiO2 over gallium nitride layer, and then continuing growth, and it would come up and laterally grow over that oxide layer. And this is an example of that. You can see very nice clean defect, well, relatively defect-free material on top of the SiO2. This E-log was developed at North Carolina State, but others at NEC, and then Nakamura really just kind of ran with a football on this one. He just took it to town and used this for the laser technology. He just did great things with it. So highlights of challenges for gallium nitride laser research include it was a lattice mismatch system, so it limits the range of cladding layers and compositions and thicknesses that you could work with. Lack of a suitable substrate, of course everybody knows this. High dislocation densities, reliability concerns, and high quality facets are difficult. Large effective masses, both in the conduction and valence bands, so this leads to very high carrier and current densities required for optical gain. Low differential gain. Large acceptor activation energy, so this made it a struggle to get a good P-type doping. especially for both series resistance as well as POM contacts, and it led to very high voltage operation. So you look at this list and you go, why would I ever want to work on gallium nitride? This is never going to work. Well, the reason a whole bunch of people joined the race and started looking at gallium nitride lasers was because of this. Nakamura, introduced the first gallium nitride blue laser in December of '95, introduced to the world that it could be done, and really inspired everybody to start working on it and push the technology ahead. And this was, the LI curve here, clearly lasing 1.7 amps, 1 microsecond pulses, 1 millisecond rep rate, and you can see the voltages here. You're looking at 20, 25 volts, so you're going to have a hard time getting this to CW. But nevertheless, I think this is really what motivated the HP Labs, I know, to start looking into working on gallium nitride blue lasers. And so that whole effort was really spawned by this. Nichia's early laser structure. This is not the earliest, what I just showed there, but when he quickly moved on to a ridge waveguide structure. You see this the electron blocking layer here. It used dry etch facets. These figures look familiar to you, or is it all blurred? Yeah. C-phase sapphire substrate. This was very common substrate that a lot of people ended up using. So if we just kind of look at a list here of other players in the field, this is a couple of years later, and at the end of 1998, I just compiled a list of other people that were working on this. Of course, Nichia was at the top here, December '95. Then Meiji University in June of '96, they demonstrated pulsed operation, and Toshiba got room temperature pulsed in September of '96. Then Cree came along in June of '97, and Fujitsu and UCSB in September '97. And UCSB was actually the first U.S. group to actually demonstrate lasing on a sapphire substrate. Cree was actually on silicon carbide substrate, and I call that cheating. So on sapphire, which was much more difficult, UCSB was the first. And then Sony and Zrock came along in October, and we were a month after that in November. So really the 97 was when people really were able to at least just demonstrate something. Still nothing compared to what Nichia was doing. And a little bit later, STL and Pioneer as well joined the race. So just as I'm showing some of these next slides, just want to keep in mind that some of the parameters of interest that people would like to do for commercialization. You want threshold currents to be in the 20 to 50 milliamp range for DVD players. Threshold voltages, you like them to be low, maybe not 2 to 3 volts, but low. Output powers need to be in the tens of milliwatts for some of these DVD laser applications. And of course, there's some high performance specialty applications that have different requirements. But if you look, I just went ahead and took all of your papers and compiled all of the threshold currents that were reported in all of the different publications. And the first thing to note here is just the number of dots. I mean, it was a publishing machine. I mean, they're just everywhere throughout this entire 3-year period. I mean, just look at the number of papers that were published. And if you look at the threshold current, what happened? I don't know what happened in 1996, but you figured something out. Because it went from 1.7 down to 350 milliamps, and then by the time you get to the middle of 1998, you're down at 16 milliamp threshold, 1.2 kiloamps per centimeter squared, which is just crazy in a 2-year time period. In addition, threshold current densities, they kind of stayed around here, a little noisy, but in the end, dropped way down. This is an example of your blue laser with the LI curves, LIV curves, and look at the voltage here. Looking at 5-volt thresholds, 50 milliamp current thresholds, and output power is greater than 30 milliwatts. Didn't even bother to mention what the peak was. It was just, whatever, it's good. Now, if you look at other quasi-CW players, and I say quasi because all of the CW lifetimes from all the other players that reported at the time, up until the end of '98, had CW lifetimes all less than a minute. So, and we'll show what Nichia had in just a second. But you see that the gray circles are where CW operation was achieved by these companies. Cree got it in early '98, and Sony in mid-'98, and Fujitsu near the end of '98. But again, if you look at the threshold currents that they got CW at, you're looking at hundreds of milliamps. So nothing even close to what Nichia was doing. As an example, I'm going to run through a few of the different players' structures in this type of format. You see Cree had their blue laser. This is kind of not their first one. This is just kind of state of the art in circa 1998. They used silicon carbide substrate, as I mentioned earlier. It was a stripe waveguide, so this would have high thermal problems, so not the best for CW, but they did have cleaved facets. At the time, their lowest thresholds were about 100 milliamps. pulls 600 milliamps CW, 15 volt thresholds is a common theme across all of the next plots I'm going to show you. A couple milliwatts of output power, even in pulse mode. So not, and when you look at Nakamura's results compared to these, there's no comparison. Fujitsu, it's kind of a similar thing, 300 milliamp thresholds, look at the voltage. Very high voltage, this was clearly a big problem for everybody. But they did achieve CW with HR coatings at 250K. I don't know if you call that room temperature now. They probably did. Then here we go, UCSB's blue laser, circa 1998. This is Aber and Mac reported this. This is a summary. I'm going to pull this from, not from the first publication they had, but they use both C-phase as well as A-phase sapphire substrates. And the nice thing on the A-phase sapphire was that they were able to use cleaved facets, as shown here. For the C-phase, they were using etched facets, RIE etched facets here. And here they were able to, 420 nanometers, 650 milliamps was the lowest threshold they were able to get to at the time. 19 volt thresholds, again, very similar to everybody else. And, but nice output power, 67 milliwatts was the max at the time. And Sony, very similar story. Look at these thresholds, actually a little lower than others, maybe in the 10 to 12 volt range. I don't know what's going on here with all this power before threshold, but I guess and I don't know what happened up here. It's kind of strange to lie, but anyway, they also got decent results compared to other people. 280 milliamp pulse thresholds, 500 milliamp CW. Not very high output powers, but decent threshold voltages compared to other people. Zrock's blue laser, again, same story, very high voltages, thresholds in the 1.7, 1.8 amps initially. Later got down to about 740, 750 milliamps. Output power is 50 milliwatts. Again, low thresholds were about 19 volts, so not very good. And HP, we were in the same situation. We had pretty bad IV characteristics. We couldn't figure out how to get good contact resistance and good low resistance through that algan layer. And we just couldn't figure out, we didn't know what Nichia was doing to get such good IVs. You know, thresholds, we got down to about 300 milliamps. Threshold voltages, 14 volts. Output powers in the 100 milliwatt range, pretty comparable to what other people were doing. So Nichia's amazing progress too. So before I show the threshold current density, and then I'm going to track the CW lifetime of the parts. In 1996, there was not CW. The red curve tracks CW. If you look at the voltage, you can see that the transition, what really made the difference for CW was dropping the voltage down from 20 volts down to 10 volts, and actually at CW actually got it below 10 volts. So that was really the key to getting to CW operation. And it was in this time frame that he transferred from a stripe laser diode structure to a ridge laser diode. So that definitely helped bring down the voltage. So he was able to get to CW with that. In addition, at the beginning of 97, introduced silicon doping into the multi-quantumals, and this really helped. Apparently, the lifetime, we're talking about 10 hours, close to, well, actually a little less than an hour here, and above 10 hours here. And these different dots here are still using C-phase sapphire, but at a later point, sometime near the end of, or in the middle to the end of 97, I transferred over to using thick E-log structures, and also transitioned to using modulation doped superlattice structures for the P cladding layer that improved the P doping levels to even drive the voltages down more. And you can see that he was able to get up to extrapolated to greater than 10,000 hours. The plot here is about 6,000 hours of CW lifetime. And this is an example showing CW for 2 milliwatts, constant power at 20 C. Current was up about 80 milliamps. They're getting over 6,000 hours. I mean, nobody could touch this. This was just way beyond anything other people were doing. So the evolution of Nichia substrate was started on a sapphire substrate with this low temperature buffer layer, then went to E-log. Defect-free regions are the regions where you would make the laser structure, and then eventually went to something where they grow a thick layer on top of this with HVPE, and then they would polish off the substrate and be left with effectively a gallium nitride substrate. So Nichia's amazing progress 3, so just keeps going. So the CW output power and quantum efficiency metrics. The power started pretty modest here, milliwatt or 2 in 97, and then up to 50 milliwatts. And then eventually, as you made a transition from atmospheric pressure growth to low pressure growth, we ended up getting up to 420 milliwatts of CW output power. Quantum efficiency of this guy was up close to 40%, which is pretty remarkable. And this is actually using an uncoated facet on one side and an HR coating on the other side. And this result here is with a gallium nitride substrate that I just mentioned before. And so this is an example of the high power blue laser, 420 milliwatts, 11% wall plug efficiency at the time. I think you were telling me earlier, 30% is now the record from Nichia. So yeah, but even back in '99, 11%, that was pretty remarkable. So if you just catalog a summary of the best results from the different groups, there's really no comparison here. The threshold current, Nichia is 16 milliamps. Everyone else was in the hundreds of milliamps. Only a few of them were getting CW operation. And this is a funny one here, 6,000 hours, 30 seconds. So, you know, at the time, there was just, it was really a race per second. There was just no one who could touch Nichia at the time. Threshold current densities, again, in the tens of kiloamps per centimeter squared for everyone else. For Nichia, 1.2 kiloamps per centimeter squared. Output power, 420 milliwatts compared to 1 milliwatt here for CW. And in pulse mode, people were getting high powers, but that doesn't really count. CW power is really what's impressive. And then threshold voltages, 4.3 volts compared to everybody else that are above 10 volts. And really, this was a big key for you know, some of the things that Nichia did to get to CW, good CW performance. So, and the culmination of all this was, actually I was preparing the slides in December '98, and I was kind of finishing them up in January '99 when Nakamura sent out this email to everybody. I'm not sure who was on this list, if it was the world or what, but this announcement that you're going to start sample shipments of InGaN-based violet laser diodes. We announced the commercialization of first InGaN-based violet laser diodes through Japanese Nikkei Sengyo newspaper yesterday on January 12, 1999. And so this was really the commercial end to all the work that Nakamura had started in the late 90s. So that was the end of the '99 talk. So now I'm going to kind of transition and just talk about a bit more a different flavor here, just some headline news stories of things. And so basically, if we fast forward 5 years, I gave the talk internally at Labs again, so I kind of refreshed a few things and just went back and gathered a few news articles. And just to show that, you know, in the years after '99, Sony, NEC, they started marketing violet lasers. Sanyo, in the picture, they got a 35 milliwatt blue violet laser. Toshiba develops 200 milliwatt laser. Sony at Photonics West in 2004 had very nice LIs. You can see nice low voltages here. Somehow they figured out Nichia's trick, I guess. Threshold currents down below 50 milliamps. Progress in the US, I think Zrock, Cree, they were finally able to achieve laser lifetimes that were somewhat respectable in the 1,000-hour range. Xerox also was able to achieve CW 20C with nice output powers. But I don't think anything has been marketed, as far as I know, from them, or was at the time. And as a result of that effort, the DVD market started expanding. And so blue laser standards were established. Blu-ray disc player was born, of course. So this, you may not know, but the Blu-ray disc player is due to Nakamura. So if you watch movies at night on your PS3, you can thank Nakamura for that. You know, Philips demonstrated the laser-based optical drive, so people started making the drives that would be associated with the lasers. Nichia partnered with wait a minute. Nichia partners with Sony in 2002. Maybe that explains the LI B curve we saw earlier from Sony in 2004. I'm not sure, but I suspect as much. So, and then, you know, Sony started marketing their blue laser-based DVD. NEC as well, their HD DVD format. Well, oh well, you can't all be winners. For those that don't know, the HD DVD format was a failure. So Blu-ray took over, and then Toshiba and others also followed. And then so gallium nitride laser diode market was set for explosive growth in 2004. With 270 million was anticipated by the end of 2008. Nichia doubled their profits in 2004. A lot of that due to Nakamura's work. All of it due to Nakamura's work. So what happened to Nakamura? I don't know. I think you all know. In 2000, Nakamura joined UCSB, thankfully for the people here. He decided he wanted a change from working in Nichia. And here I just have a couple of quotes from him that I pulled at the time. It's from the Nikkei Electronics Online. The quote here, the more I fall into the quagmire, the more ideas I get. And then the question was, you've decided to move to the US because you saw that there were limits to the Japanese system and did not fairly assess the achievements of individual engineers. So the answer was, I feel stronger than ever that Japan lacks freedom. Here in the US, there are no rank relationships when doing researches. This country truly operates on the merit system and liberalism. And so I think he was kind of ready to move on from Nichia and do something different. You probably don't remember these, right? Is there a possibility that you'll work for a large company if you get a good offer? I mean, this one tickled me. Absolutely not. Nothing good comes from working. I was working in HP at the time, so. And then there were some legal disputes with Nichia. And there's just one quote here that I wanted to pull from that. The Japanese court in January 2004 ruled in favor of Nakamura over Nichia in a lawsuit. And I like this quote from them. They said, Nakamura deserves the amount he got because the invention was a totally rare example of a world-class invention achieved by the inventors' individual ability and unique ideas in a poor research environment and a small company. Someone in the Japanese court really didn't like Nichia. So if we flash forward 10 years, I think the Nobel Committee actually agreed with the Japanese court and awarded Shuji the much-deserved Nobel Prize in 2014. And there is a little audio here. I'm not going to play it, but if you go to the Nobel Prize webpage, you can hear his response. It wasn't the original. I thought when I clicked on this, I thought it was like, oh, I'm going to hear like when they originally called it. That would be cool, but it wasn't. But it was shortly thereafter, so it's kind of fun to listen to if you want to take a look. But anyway, I also wanted to mention that Nakamura wasn't the only one that got this Nobel Prize. He shared it with Akasaki and Amano. And so I wanted to just briefly mention what they're doing on the list. So Akasaki in 1973 was a professor at Meiji University. And throughout the last half of the 1970s, researchers abandoned the unexplored semiconductor research of gallium nitride. And so this is from their webpage on the Nobel Prize side. Feeling like he was walking alone in a wasteland, Professor Akasaki worked on gallium nitride crystal growth day and night. And one day he saw a tiny crystal under his fluorescent microscope that gave off cobalt blue light and became convinced of the major possibilities of gallium nitride. So that kind of really got the ball rolling in the late 70s. Then Hiroshi Amano, he joined Professor Akasaki's group in 1982 as an undergraduate student. How cool is that? In 85, probably still as an undergraduate student, he developed low temperature deposit buffer layers for the growth of group 3 nitride materials. Did any of you do that for your undergrad? Anyway, and I think you also independently developed a low temperature buffer layer growth technique for gallium nitride. And then in 89, he also succeeded in growing p-type gallium nitride, fabricating PN junctions for the first time in the world. And also, likewise, Nakamura independently developed a method for growing p-type gallium nitride and making PN junctions. And so, of course, Nakamura, here he is toasting with Herbert Cromer. You've probably all seen this picture. But I like this. Nakamura also said he did not anticipate developing the blue LED from the outset of his research, but rather started with the goal of simply getting a PhD. Don't we all? So my dream was to get a PhD. At that time in Japan, by submitting several scientific papers, you can get a PhD. You don't have to go to university. So at the time, my dream was to publish 5 scientific papers, not the blue LED, Nakamura said. So I think we can say your dream has been satisfied, and then some. So anyway, with that, I would like to close. Just again, honor Shuji Nakamura for getting the Nobel Prize.
Questions, comments?
Oh, not bad. And you were worried. 82 slides.
82 slides.
Scott, I have a question back here. So with your deep knowledge of both, conventional gallium arsenide and indium phosphide lasers and the upcoming of gallium nitride, I'm sure you're familiar with the SHEDS program and gallium arsenide reaching efficiencies in the 70%.
Yeah, you can just tell me about this. I actually haven't followed the gallium nitride laser research
So that
for the
was
past 10 years.
That was gallium arsenide.
Oh, I'm sorry.
So where do you think GaN is, or where GaN can go compared to these, what you call more standard
Yeah.
lasers? Do you think there's a limitation, a fundamental limitation on efficiency, or?
You know, I'm really not the right one to answer that question. This is probably the right person to answer that question.
No, James knows better than me now. He's working for it today, right?
Yeah, no, honestly, I haven't been following the field for 10 years, so I really don't know what's been happening in gallium nitride lasers. So I can't really answer the question.
That's always a hot question,
Very well.
because gallium nitride right now is in the 30% range for efficiency, and gallium arsenide is double that.
Yep, yep.
So people, want to know.
Are questioning whether you can really
Yeah.
make it work. Yeah, it's the question of the day. I'm sorry, I can't provide much insight.
Anybody else?
So you mentioned at the very beginning, it seemed like people, when gallium nitride got big, abandoned solenoids.
Yeah.
Did anyone, I mean, did they kind of figure out whether the problems with reliability and lifetimes for the solenoids were like a fundamental property of the material, or, I mean,
Yeah.
is there any point in going back and looking at those materials, especially because we're looking at green devices?
So, my response is going to have to be from what I knew in the late 90s. I actually don't know what's happened with 2.6s since then, but at the time, even at the time, people were really questioning whether it was going to work. A lot of people put a lot of effort into trying to make 2.6s work, but they just really struggled with trying to get the reliability up and just never got it. They're softer materials, and there was never a breakthrough like what we had. Maybe if Nakamura was working on 2.6s, we would have them working. And then the thing I think about it is that it's very possible that a gallium nitride and InGaN system could have gone the way of zinc selenide if you didn't have somebody who actually figured it out and was able to make it work and demonstrate long CW lifetimes. It might have been the gallium nitride laser development would have just faded away without some of the contributions such as what Nakamura made. But I personally wouldn't work on 2.6s.
2.6 is basically ionized bonding. Ionized bonding with their water, it's easily dissolved. That's the biggest one. So there's some water there, easily degraded because the bonding is spicy. So that's the biggest one, ionized bonding. Because the nitride bonding is very, very strong.
Very strong.
Yeah.
Who else? You can get any question answered here. Still have like 5 minutes.
What was the, how discouraged were you guys at HP when you were working and seeing how far ahead Nichia was? Was it a concern that you were always going to be behind, or you thought?
Absolutely. Yeah. Oh yeah, I mean, you really felt, I think we all kind of conceded that he was like so far ahead of everybody. We were all convinced that he had a secret that we didn't know, and that we would stumble upon it sometime, and I think probably everybody thought that, and we never did. But yeah, it was hard. And also, we were talking earlier, is that the consistency of the growth in our reactor was not very good, and so that was discouraging as well. And so when you don't have consistency in the growth of the reactor, it's really hard to make progress because you don't know what to attribute. If you run a matrix of different experiments and they all come out just all different, but you don't know if it's because of this one parameter you tweaked or not, then it gets difficult to make progress. And so we definitely were frustrated with the reactor and our inability to get very consistent results. The uniformity of the wafer across the wafer was hard. And so, and then you see Nakamura just whipping out one paper after another. Incredible, improvements each time he would come to a conference. Now, I've heard a story, I don't know if it's true, but in one of your blue laser conferences, you actually used a blue laser pointer.
Yes. At the time, extron, we tested the extron reactor and the big reactors. Oh, reproducibility terrible. And so we complained to the big and the extron. And they said, please keep confidential. We want to, purchase the reactor from your company. So basically, we tested and we gave up. It's free. But they want to keep confidential everything. So that is a problem. So the reactor is this one. So
yeah.
I have a question for Shuji. So for all these grad students in the audience, what's the problem that's equivalent to 1992 of making a gallium nitride laser? What problem would you work on today if you were a new young grad student?
For graduate student,
And what's the big unsolved problem in your opinion?
biggest problem in 1999.
Today.
Today, for laser diode,
For anything.
anything.
You can limit it to laser diodes, that's fine.
Laser diode, you know, yeah, a lot of combinations. So right now, nitride, LED is just Drup is a problem. Drup is basically, Jim found that it's called the OG combination. So it's an interesting problem. So means LED has an interesting problem to improve the Drup. No way not to do solve the problem Drup. So LED means some kind of limitation. So now, at the university we are mainly working on laser diode now.
So this is why lasers are better. They don't have droop once they hit threshold. It's
Yes. So now it is more exciting. Because OJ information is interesting problem. So nobody can solve the problem of OJ information. You know, for communication, long way because it is there. Still, OJ is the biggest problem.
So Scott focused on other substrates because back then that was a big thing.
Yeah.
But now there's a lot of gallium nitride and silicon for these power electronics. I know you like gallium nitride substrates, but what's your opinion of prospects for gallium nitride on silicon?
Nice. My opinion, no mention. I think Gamma is best, no doubt, because I think, see that? Yeah. I think I'm really expect to make a large gallium substrate in the near future. With a decent price, so I think Gamma is the best for everything. Right? No mention. No mention Gamma.
So you think you blue silicon
You've done
photonics?
ELO, you could do ELO on silicon.
No, you do the big strain, curvature from all kinds of processing is so complicated. The yield is almost zero. Already okay, but to make product error doesn't work. So the same thing, Gamma is a huge growing storage, all kinds of process power. I think it's hard. Yeah, Gamma is not the best.
Who else? So I can remember going to conferences and Shuji would show this result that was really, really good. And then he would say, I think there may be a better result coming up with the next one. Of course, he had already measured, but he hadn't yet. He wasn't ready to.
No, next is James Group.
Talk about it, yeah.
James, what's it? No, it's
Non-polar, semi-polar is next, right, Shuji?
yes.
Are we all finished? Okay, let's thank the speaker again.